Hello and welcome back. So, in the previous class we talked about particle size distribution and how you can measure it from a given particle size analysis. And if you remember we were talking about these two kinds of representation of the same data when you describe the particle size distribution. One is through a histogram or a frequency plot like this, and another is a cumulative plot like this. Okay. So, this cumulative plot will be obtained if you add up the previous sizes and then plotted as a function of cumulative percent finer. The same data can also be plotted the other way, for example, as a function of cumulative percent larger. Okay. So, either the size above a given size or the size below a given size, both can be considered to construct this cumulative plot. Okay. We can take an example and then see how it is done. So, that will give you more clarity as to how exactly it can be obtained and what we mean by cumulative. So, let us take this example. Let us say we have done that sieve analysis and collected this data. So, we have different mesh sizes. Let us say these are 70, 80, 100, 140, 200, like this. Okay. And for each of these mesh size, how much of powder is retained on each of them, we have already got that data from the sieving analysis. So, let us say it is like this. So, here you can see the total weight is 77.5 gram. Okay. So, if you calculate the interval percentages, that means the fraction of a given size, this is 0. So, this will also be 0, this one is around 1.3%. So, these are the interval percentages, and now if you take the cumulative percent, you can simply add up for a given size whatever is before that, you can add that up, or whatever is below this you can add it up. So, here you can see the size, since mesh size is increasing, the particle size is actually decreasing in this case, right, as you go down. For example, the corresponding size in micron for 70 is 212, and for 400 mesh it is 38 microns, right. So, the cumulative percentage would be as follows. Okay, so like this, when you add up the interval fractions before a particular size or below a particular size, then you get the cumulative percentages like this. Okay, and that is how you will obtain the cumulative plot like this. And it is typically an S-shaped curve like this, and from this you can also derive the statistical information like the median size corresponding to sigma equals to 0, then the sizes corresponding to sigma equals to 1, sigma equals to 2, and so on, where sigma is the standard deviation. All right. So, that is how the cumulative data can be represented for particle size distribution. And one thing I must mention over here is that when you are representing the cumulative plots, it is important to specify the basis for the distribution, because what we have seen is that the data is collected based upon a different basis, like it can be population based or it can be weight based. In this case, when we are doing the sieving analysis, right. So, that is why when you are representing the distribution plots, this cumulative distribution plots, it is important to specify what is the basis, because a given basis will give you a particular type of data which may not be identical when the same data is being recorded using a different basis, right. Like here, for example, you can see these are the two plots which represent the same data of particle size distribution of a given powder, but since the basis is different, one is population, another is weight, they are not exactly the same, right. Although the trend can be same because it is collected from the same powder sample, but since the basis is different, they are not exactly identical, right. So, this is why when you plot it and represent the data, you should also mention the basis. Okay. And therefore, it is also true that the distribution determined on different basis cannot be compared, right, because as I said, they are not going to be identical. Now, this is a kind of plot out of all this that you see over here. This log normal is a kind of distribution which is encountered very often, and that is what that is why you are going to look at it in little more detail right now, because as I said, most powders exhibit a log normal size distribution that will give you that bell shaped curve that we have seen over here. And if you want to describe this distribution mathematically, a Gaussian probability function can be used to describe it, and which is given over here, wherein Px is the probability of observing a particular size. Okay. And in this expression, u is the natural log of the mean size, and if you use a linear x axis, that will give you a kind of skewed distribution, whereas a log scale will generate the exact bell shaped curve like what we have seen here. And cumulative distribution that we talked about just now can be represented by this. So, as we have seen, this is a summed up representation of the data, and that is what you see over here also, that the data is summed up from a particular size to a given size x, or over a particular interval from 0 to x. And if you plot the standard deviation, which is this, against the log of size, that will give you a linear curve. I will come to that in a little while. And that particular curve is known as log normal plot. Okay. And from this curve we can derive information like the intercept will give you the mean particle size. And the advantage of the log normal plot is that the distribution obtained from different bases can be compared now, which was not possible like how we discussed a little while ago for the cumulative plots. Okay. So, this is how it will look like. It will, as I said, it will give you a straight line, the plot between standard deviation and the log size. And now, in order to compare the data which is collected from different using different bases, this is what you can do. You can simply note what is this delta or what is this difference between these two plots, that is it. And once you note that shift, the data can be easily compared, right. And the delta is given by this expression that you see over here. Delta is equal to 6.908 by m, where m is the slope, right. So, now that you know the slope, you can easily calculate delta, and you can simply make a note of that. And once you know that, you can compare different data collected using different bases. Okay. The median size MD is calculated with the help of this relationship over here, where B is the intercept for weight measurement basis, and m, as I said, is the slope of this straight line that you see over here. Now, if you want to calculate the median size for another basis, for example, the population basis, that can be simply obtained by adding this delta value, right. And therefore, the MD or the median size for the population based data would be 10 to the power minus B plus delta by m instead of B by m, right. So, that is what the advantage of this. As I said, you can compare data from different bases by simply knowing the shift between them or the delta, right. Okay, so, we have seen in last couple of classes now that how the particle size and the particle size distribution can be obtained for a given powder sample using certain techniques. So far we have only discussed about two techniques just to demonstrate on what basis the data is collected. So, we have seen two bases or just examples of two techniques which collect the particle size data based upon two different bases. One is weight, which is the screen size analysis, and another is the population, which is the microscopy based analysis. And we have seen how you derive the particle size and the particle size distribution from the data. Okay. So, before we close today's class, let us quickly summarize it. First of all, the particle size techniques use a particular basis to do the analysis of particle size measurement. That is the first important point to note about particle size measurement. And in these two classes, in previous two classes, we have seen two examples of that. One was this microscopy based technique which is population based, and the other one was this screen or this sieving technique which is weight based. Okay. In one case you plot the data as the weight percent for a given size, and in the other case for the microscopy based technique, you plot the count. Okay. So, that is exactly why it is known as the population based method, because you actually report the population or the count, that is the number of occurrences of a given size. Okay. So, that count is reported or plotted as a function of the particle size, right. And then as far as the particle size distribution is concerned, we have seen there are two ways of representing it. One is through the histogram or the frequency plot, and another is the cumulative plot, where you sum up the previous particle sizes or particle size above or below a given particle size, and that kind of plot looks like this, a typical S-shaped kind of plot is obtained when the cumulative data is plotted. And here also the important point to note is the basis has to be specified, because the particle size distribution data determined from different bases cannot be compared, because they are not identical, right. You can see that the population based data move towards finer size compared to weight basis. Okay, that is what you see over here if you compare these two plots. And therefore, as I said, it is important to specify the basis when you are representing particle size distribution data. And the other thing that we discussed today was this log normal distribution, because this is the most commonly occurring distribution that you can encounter in a given powder sample, and mathematical expressions for that is also given here, both for for a given probability and also for the cumulative data. And when you plot the standard deviation as a function of the particle size, then you get a straight line like this, and in that case the data from different bases can be easily compared, because you can get this delta or this shift between them with the help of this expression, where m is the slope. Since the slope is known, delta is also known. So, once you know that delta, the size obtained from one particular basis can be easily converted to other basis by simply adding up that delta. Okay. So, that is what we have seen here, okay. And that is how you can represent different bases and obtain the same information of particle size using different techniques which might use a different basis, right. So, with this we come to the end of this class. Thank you for your attention.